In this video presentation, I'm going to talk about a result that we published last March in Physical Review Letters about the foundations of quantum mechanics. The idea is that we showed that one of the four postulates of quantum mechanics, in particular the one that the composite system is described by the tensor product, is redundant in the sense that it can be recovered from a basic definition of what a composite system is in physical terms and from the other postulate of quantum mechanics. This is something we worked on during our sabbatical in Italy, and we collaborated with Lorenzo Maccone from the University of Pavia. The talk will be divided into three parts. First is going to be the setup, in which we talk about what is the role that postulate plays in physical theory and what it means to remove them. And we'll talk a little bit more in detail what are a composite system and what kind of properties they need to have physically and how we're going to encode them in the math so that we have a clear mathematical specification of what we need to do. In the second part, which is going to be the more technical, we'll go through the proof. We're not going to go through it in complete detail, but we'll hit the main points that also gives us a little bit more understanding of the mathematics that is used in quantum mechanics. We see, for example, that projective spaces are actually where the physical information is encoded, and we'll see how they can bridge the probabilistic event that we have in the quantum description with the quantum states themselves. And then we'll see how the fundamental theorem of projective geometry and the universal property of the tensor product help us mathematically to reach the goal that we want to reach. In the last part, we'll step back and we'll talk about more general problems. There are two things, for example, that have confused some people reading the paper itself, so we're going to talk about them, and that's will sort of hint that there is a bigger problem, that there is sort of a mismatch between the mathematics that were used in quantum mechanics and the physics that math is supposed to represent, and that creates some problems and confusion. So let's dive right in. The first thing that I want to clarify is how I think relationship between physics and math is in the current formulation of quantum mechanics, right? So we have the physics on one side and we have the math on the other side. We have some physical objects, for example, the state of a quantum system. This is something that exists in the real world, it's something that we prepare in a lab. And then we need to represent this mathematically. And we have a postulate that tells us that this physical object, the state of a quantum system, is represented by the math, in the math, by a ray in a Hilbert space. So the postulate basically tells us how to represent mathematically an object that lives in the physics world. And it doesn't tell us why that happens, it just says that that should be the case. So we have another postulate, for example, that takes quantities and measurements, and again, these are something that exists in the real world, and it tells us, well, mathematically in the theory, we have to represent them with Hermitian operator and the Bohr rule and projections and so on. And again, we don't know why that is, it's just the postulate tells us we have to do it like that. There's another postulate that tells us the composite quantum system should be represented in the math by the tensor product, and that time evolution should be represented by the Schrödinger equation. Okay, so the postulate basically tells us, look, there are these things that exist in the physical world, and this is how we represent them mathematically, without telling us why. So what does it mean for us to remove a postulate? Well, the idea here is that a composite system has a relationship between state and quantities, right? So it's not something that is completely isolated. It's not a new physical object. It's something that has links with the other things that we have here. Well, in the same way, the mathematical representation will have to have those same relationship to the representation of the other physical objects, because otherwise the composite system representation wouldn't be really representing the physical relationship that we need to represent. So the idea is that if we can characterize enough of the quantum system, the properties the quantum system needs to have with respect to states and quantities, and we are able to encode those properties in the mathematical language such that the mathematical representation has to have those properties. If we do that enough, then we do not need the postulate anymore, because we're able to identify that the tensor product is the correct mathematical structure to do it. We don't need a postulate to arbitrarily tell us that that's the right mathematical structure. We know that that's the right mathematical structure, so it's not a postulate anymore. It's just something that derives from the physical requirements that we have. So that's what we want to do, and that's what we're going to do. So here's the recipe that we want to follow. We want to identify basic physical requirements that a composite system must have to be physically meaningful. We want to translate those requirements into mathematical definition. And then we want to show that the use of the tensor product to model a composite quantum system follows mathematically from those definitions and the other postulates. And if we're successful, the postulate is no longer necessary. The physics is enough to constrain the math. So the first requirement that we're going to have is preparation independence. And what do we mean by preparation independence? Two systems are said independent if the preparation of one does not affect the preparation of the other. So I can take system A, I can put it in any state that I want, and when I take system B, I can also put it in any state that I want, regardless of what state I chose for A. By the way, this numbering system that we use is the same numbering system that we use in the paper, so the idea is that if you read the paper, you're going to be able to follow along with these symbols. Okay, so that's a simple enough physical requirement, but how do we express that in the math? So ultimately, the physics of quantum mechanics is expressed in probabilistic terms, so we should formalize independence in terms of probability. And how do we do that? Well, suppose that A and B are the state spaces for two quantum systems, A and B. Now, two states inside those spaces are compatible if the event, the proposition A and B, that is, the system A is in state A and the system B is in state B, is possible, which in probability language means that it does not correspond to the empty set in the sigma algebra. So it's an object to which we can assign a probability. And two systems are independent if all the pairs are compatible. So if all the pairs exist as a non-empty set in the probability space. So that's easy enough, but you might see that we are using this underline under some of these symbols, and that's something that we have to discuss because it's going to be important later. So typically we think about the state space of a quantum system as a Hilbert space, and we have a vector, and a vector represents a quantum state. And the issue here is that this is not technically true. The vector is not a quantum state. It's the ray that it's a quantum state. So we can take any vector and multiplying by a complex number, and still that represents the same state. So the complex number will change the phase and the norm of the vector, but the phase is completely irrelevant and the norm is something that we renormalize anyway. So the same, all the vectors in the same ray really represents the same quantum state. And the rays are actually objects, they are points in what is called the projective space. So we're going to put the underline in all the objects that are in the projective space where we have removed, where we have quotiented out the complex number. Now we can see that all the physics is actually in the projective space, because if we look at the probability rule, the Born rule, they are going to be independent of a k factor. So if we multiply these vectors by k, the probability is still going to be the same. So really the probability is between the two rays and not two particular vectors. Another notation that we're going to use is the span. If we have a bunch of vectors in our vector space, we can take the span, which is the space that represents all the possible linear combination of those spaces. And of course, we're going to have an object in the projective space that is the equivalent, right? And we are going to have the span underlining means that it's the set of all the rays that represent the span. So this distinction is going to be important and is going to be the main source of troubles when we're going to go through the proof, because all the physics is going to be specified in terms of the projective space, but the result that we want, the tensor product, is something that it's about the Hilbert space. So we're going to have to take things that we say about the projective space and push it back down in the Hilbert space. And that's going to be technically the most difficult part. Okay, so for the second requirement, we have to specify exactly what is a composite system. And logically, given two systems A and B, their composite system is the simple collection of those and only those systems. So you can think it as the smallest system that contains both, right? So this is a very intuitive way to think about it, but again, how are we going to specify that in a mathematical language? So we'll break this down into two requirements that do not fully specify what a composite system is, but it tells us that a composite system at least must have these two properties, and then it turns out that these two properties are actually enough to get the result that we want to get. So the first property, that stems from the fact that C is made of A and B, basically tells us that whenever we prepare A and B independently, we actually have prepared a composite system. We have prepared a state of C. So if C is the state space of the composite system of A and B, then there must be a map M that from each pair of states A and B gives us a state C. And it has to be that saying that I prepared the system A instead A and I prepared system B in B, it has to be the same statement, has to be the same event in the probabilities than saying I've prepared C in the state MAB. Now the second part is going to come from the fact that we only prepare A and B. And if we only prepare A and B, it means that given any state of C, measuring A and B independently must lead to a pair of respective states with non-zero probability. So if we prepare C, we must at least in some cases be able to find A and B. So formally, for every state C of the composite system, we can find at least one pair of states A and B, such that the probability of finding A and B, given that we prepared a C, is different than zero. So again, you might think that a composite system might actually have a stronger requirement than that, right? But it turns out that that's enough, so we don't need to require more. So let's describe this a little bit with a diagram, what happens mathematically. So we have our Hilbert spaces of our system A, system B, and system C. We have our projective spaces that represent really the state by removing the phase. And we're basically saying that there must be a map that whenever we take a state of A and state of B, and we can put them together and collect them to form a state of C. What we want to prove, what we want to show, is that there exists a map M on the Hilbert space such that we can go this direction or we can go this direction and we get exactly the same result. And we want to show that M not only exists, but it can be taken to be the tensor product. So our goal is to show that the Hilbert space of the composite system of two independent quantum systems is represented by the tensor product of the Hilbert spaces of the composite system. So mathematically, we want to show that there exists a bilinear map little m from A, B Hilbert spaces to C Hilbert spaces, such that when we take a vector A and a vector B, apply M, and then take the ray, which is the state, is the same as applying M directly to the rays. And we can take that map M to be, without loss of generality, the tensor product. If we are able to do all of that, the tensor product is not a postulate anymore. We know why that is the correct mathematical structure to use to represent composite system, and we don't need something else to tell us why. In fact, it turns out that we are going to understand a little bit better the structure of quantum mechanics and Hilbert spaces by doing so. Okay, now for the more intense part of the presentation, the proof. The proof itself is quite complicated and we're not going to go through all this. If somebody wants, they can go through it in the paper. But this can sort of serve as a guide to read the paper so that you know what are the highlights and the important points. So we break out the final goal into three intermediate conditions, three intermediate hypotheses. The first hypothesis is that M is a total function, which means that it's defined on all the pairs of A and B. The second hypothesis tells us that if M exists, it must be a bilinear function. That is, if we do a linear combination in the first argument, we get a linear combination, or we can do also a linear combination on the second argument and we get a linear combination of the result. The third hypothesis is that M is span surjective. And what does that mean? If we take all the pairs and we apply M to all the pairs, we're going to get a set of rays. And then we want to say that the span of all the rays, all the possible linear combination of all the rays that results from M actually cover the wholes of C. So that's the third condition. And once we're going to have these three conditions, then we are going to go and prove the final result that M exists and can be taken to be the tensor product. So these two parts, the proving that M is bilinear and the last part, are the hard bits. They use a little bit of a more advanced math. So let's concentrate on these two hypotheses first. So first of all, M is total. And again, these labels that we're using are they seem funny, but they are actually the references in the paper, so that allows for somebody to follow along. So we want to show that M is a total function that is defined on all the pairs. So we saw from preparation independence that all events A and B are possible, are things that exist in the probability space, are actual objects. Now the definition of a composite system tells us that MAB is equivalent to A and B as a probability event. So if A and B is not possible, meaning it's not an object, it's an empty set, then the function M would not be defined on the pair because it wouldn't be able to point to any object. So M would have to be a partial function. So assuming preparation independence, M is defined on all pairs because all those points exist and is therefore a total function. So the totality of M really means preparation independence. It's a one-to-one physics to math mapping. So physically, if we don't have preparation independence, so we have some super selection rules, we will not have the tensor product. So for example, if we have two electrons, if we prepare an electron in one state, we know that two electrons cannot occupy the same state. So the second electron is not independent from the first. We can't prepare it however we want because we have to prepare it in a state that is different from the first. So if I take the state space of the two electron, we are not going to use the tensor product. In fact, that's not what we use. We use the anti-symmetrized tensor product. And this is exactly why, because two electrons are not really two independent systems. Okay, the third requirement was that M is span surjective. And what does that mean? If we take all the pairs from A and B and map them through M, we're going to have a set of rays. We're going to take the span of all those rays and we want to show that that span is the full state space of C. So let's consider the span, all the things that are reachable by essentially superpositions of things that we get from A and B. This is a subspace of C because it's a span, so it's closed under linear combination. And so our question is, does it cover the full space? Well, suppose it doesn't. Suppose there is a state that is not the span of the image of M. So we cannot think of C as a linear combination of independent pairs of A and B. If that's the case, then C is perpendicular to all elements of the image, right? Because C is going to be linearly independent from anything that we can get from A and B. This means that if we ask what is the probability that we find the combination of A and B given C, that has to be zero because they are orthogonal subspaces. And it has to be zero for all pairs A and B. But this violates the requirements for the composite system because now we are able to prepare a state C, but we never find any pairs of the components. And so this cannot be, and therefore M has to be span surjective. Now the fact that M is span surjective means that the composite doesn't have anything else inside because that was the condition that we expressed with that probability rule. And mathematically, this means that any state of the composite system is a superposition of independent pairs of the individual systems. So again, this is a necessity. It's not something that it's reasonable. It's not something that it's convenient. No, it's something that we need to have a meaningful composite system. Okay, now this is going to be the part that is a little bit more tricky. We have to understand how to get the linearity. And before we can talk about that, we need to understand a little bit more the relationship between Hilbert spaces and projective spaces. So suppose we have a map between two Hilbert spaces, between A and C. We have a map F. And suppose that that map is linear. Now, we are going to be able to take the projective space, and we're going to be able to assign, to create a map here, a map F, that essentially is the equivalent to going through other routes. So we want that going from here to here to here, and going from here to here to here will give us the same result. So this will give us a specific F. And so the question is, if this is linear, what is this? What property does F, big F, need to have? And this F has to have a property called collinearity. The F must be collinear. And the easiest way to understand collinearity is that it preserves the subgroup structure. That is, if we have G1, and G1 is a subgroup of G2, then F of G1 is a subgroup of F of G2. So everything that is a subgroup remains a subgroup, things that are orthogonal remain orthogonal, and so on. Since we're going to want to Rm between A and C when we make a composition, we will want this to be bilinear, meaning if we fix one side, this part has to be linear. Then it also means that M, if we fix one side, if we fix B, M will have to be collinear. So we first need to show that M is collinear, and then when we show that M is collinear, we can take advantage of the fundamental theorem of projective geometry that tells us that if this is collinear, we can go back and find a corresponding linear transformation. Okay, so how do we show that M is collinear? So if we look at the Bohr rule and we say, what is the probability of getting A1 given that we prepared A2 and B? Well, since B is an independent system, B is not going to appear in the Bohr rule. And therefore, this is going to be equal than preparing A2 by itself, the probability of getting A1 having prepared A2. So the fact that we prepared B is sort of irrelevant. Now, what happens is that if you also put a B on the other side, doing some simple probability rules, you will find that it will cancel out, and we'll just have the probability of A1 given a probability of 2, because the probability of B given B is just going to be 1. So what we'll find is that the probability of having MA1B, given that we have MA2B, is exactly the same as the probability of getting A1 given A2. But the probability gives us orthogonality between subgroups. So to sum up, the map M has to preserve probability, and therefore orthogonality, and therefore the subgroup structure. But if you preserve the subgroup structure, then the map is collinear, which is what we want. And now, since the map is collinear, we can use the fundamental theorem of projective geometry that tells us that for every collinear map, M, on the projective space, we have a map little m on the Hilbert space that it's either linear or antilinear, meaning that it's linear in the complex conjugate. Now, there is a little bit of detail here, is that we don't just use the theorem of projective geometry, we make use of the fact that we have a Hilbert space, but that's a technical detail I'm not going to talk about. The important thing is that we are guaranteed that if we have a map M, we have a map small m that is either linear or antilinear. What is important here to understand is that there are actually infinitely many map little m that induce big M, not necessarily linear or antilinear one. We pick those that are linear. We pick the one that is linear or antilinear. And this is, I think, an important detail that lets us understand a little bit more of the geometry of these spaces. So let's look at this point a little bit more closely. So again, we have our Hilbert space and our projective space. And you can think of a map M as something that maps a basis to a target basis, right? It takes this vector and maps it to this vector, and then since everything's a linear combination of the bases, once we know what happens in the basis, we know what's happening on the full map. Now, the same thing is going to happen in projective space, except instead of the bases, instead of being a vector, they are going to be rays, right? So we have n rays here that map to n rays here. Now, the issue here is that if we go from vector to rays, there is only one way that we can go about doing that. given a particular vector, we have a particular ray. But if we go the other direction, things are a little bit more complicated, because now if we have the ray, we have to pick one of the vectors in the ray, and we have infinitely many ways to do it. Even if we say that the vector has to be unitary, we have to still pick a phase. In fact, to pick a basis, we will need to pick an arbitrary phase for each element of the basis, for each base. And what is an arbitrary choice of phase for each element of the base? Well, that's a gauge. So the idea is that when we're going from rays to vectors, we have to pick a gauge. And changing the gauge, you see, is not going to affect our inner product, because we're going to have the phase with the minus and the phase with the plus, and they're going to cancel each other. And so the idea is that in the proof, we use this freedom to construct the linear map. So we fix the same gauge from the initial space to the target space, and we sort of tweak the gauge such that we have a linear or antilinear transformation. We use that gauge to get the linearity. So the linearity is really a choice of gauge. We fixed the gauge, we fixed the representation such that we have nice and linear maps. Now, the linearity versus the antilinearity is also a choice of representation, because we can formally switch the bras with the cats in all of quantum mechanics, and which would mean that basically we're using the complex conjugate on the states, and all the probabilities, all the eigenvalues of the Hermitian operators, they're not going to change. They're all going to be the same. We're going to have the same physics. So if the map is antilinear, we can always transform into the linear case, and therefore we will assume the map is linear without loss of generality. So this means that we have reached the second hypothesis, which was, as I said, the one that is a little bit more complex, is that M, if it exists, has to be bilinear. And now we have all the ingredients what we needed. We have all the pieces, and we need to put them together. But before we can do that, there is another little bit of math that we are not going to need, and so we need to spend a few minutes to understand it. And this is the universal property of the tensor product. It's something that characterizes uniquely the tensor product because it's the only thing that has this property. That's why it's called universal property. So the idea is that if we have a product space, a product of linear spaces, and we have another linear space, C, and we have a linear map, M, that goes from the Cartesian product of A and B to the space, then this bilinear map will factor through the tensor product, which means that we're going to find a map I from the tensor product to the linear space C, such that going this direction is the same as going directly to this direction. So any map M can be represented as mapping out from the tensor product. And this is exactly what we're going to use to get to the tensor product. How we do that? Well, hypothesis 2 tells us that M has to be bilinear, and so we can find a corresponding I that maps out of the tensor product. We can map first inside the tensor product in the standard way, and then go from the tensor product to our composite system C. Now, because M was span surjective, then the basis of C cannot be bigger than the basis of the tensor product of A and B. Otherwise, there will be some other part that wouldn't be the span of this map. That is, we need to make sure that inside C, there is nothing but A and B. Okay, so the basis of C cannot be bigger than A tensor B. But because M was total, I cannot send to zero any element of A and B, right? Any pair of A and B must map to an actual object of C. It can't map to the zero vector. Therefore, the basis of A and B cannot be bigger than the basis of C. And again, remember, this was just preparation independent. If we prepare a pair A and B, that has to be mapped somewhere in C. So if the basis of A and B cannot be bigger than the basis of C, and the basis of C cannot be bigger than the basis of A and B, we have an isomorphism between the two things. We have a linear map that basically makes these two things coincide. And this means that we can always think of the composite system as the tensor product, and this map I, we can just think it as an identity. And that's it. That proves us that the composite system is the tensor product. So we showed that we can recover the tensor product for the composite system based on very narrow physically motivated requirements that we have preparation independence, and the composite is made only of the parts. Now, could we use something else instead of the tensor product? Yes. We could use other maps that introduce arbitrary gauges and phase flip, and they are nonlinear and they're a mess. But why should we make our life complicated? So we'll pick the representation, the thing that behaves nicely, and that's the tensor product. It's the only linear thing that is going to satisfy that requirement. So now we know exactly, both at a physical level and a mathematical level, why we use the tensor product in quantum mechanics to represent a composite system. Okay, now that we reached the main result, let's step back a little. One of the things that I want to note is that the starting points are simple, yet the derivation is not. We have to do a whole gigantic journey to go and get to the result that we want. And there are also two details that have been source of confusion, and so I want to go through them quickly in case somebody has sort of the same objections. One of the problems that we had during peer review is that one of the reviewers objected to the fact that we could just dismiss the antilinear case that way. In fact, there are previous work, citing the previous work of Matolsky. Matolsky is going to find that there are two non-equivalent tensor products. So we have the standard tensor product and the second tensor product where we are taking the first space as a complex conjugate of the first. So there are some people that would think that these are physically inequivalent, that these are physically different. But again, this is not the case. And this is the fact that these are equivalent was also known to the founders of quantum mechanics. If we go and see the paper in which Schrödinger's derive the Schrödinger equation, he comes to two equations, and he says we will require the complex wave function phi to satisfy one of the two. And see that there is an I and the plus or minus is here. So picking one or picking the other is the choice of using the standard wave function or the complex conjugate one. Moreover, when Wigner goes and looks at the representation and it posits that there is a representation equivalent, again he says that you're going to find a linear representation between psi1 and psi2, or that you're going to find one for the conjugate imagery of psi2. And he says, although in the latter case the two representations are still equivalent physically, we shall, in keeping with the mathematical convention, not call them equivalent. And I think this is the problem. Maybe we should stop doing that. By calling them inequivalent because they're mathematically inequivalent, we lose the physics. We lose the fact that these are actually physically equivalent. And then mathematicians like Matolsky and like some of the reviewers that we had are just going to get confused themselves. Another issue that has been raised is that there is actually no tensor product on Hilbert spaces. What does that mean? Is that the characterization of the tensor product through the universal property does not actually work in Hilbert spaces. And here there is a link to somebody that goes and explains that more in detail. But in the proof, we did not use the universal property on Hilbert spaces. We just used it on linear spaces where it works. So there is actually no issue. But this comes back in the sort of the same problem, right? Which is, do we actually have the right math? Conceptually simple physical premise lead to complicated math, right? The antilinear case is not part of the same mathematical category and causes confusion. The category of Hilbert spaces does not yield a correct categorical tensor product. So the idea here is that there is a mismatch between the physical content of the theory, right, what we actually need to represent mathematically, and the mathematical structures that we use to represent it. And this is my general question, which drives the rest of my research. Should we, in physics, perhaps stop simply using the tools that mathematicians create on themselves because they need to solve mathematical problems, and maybe start developing some that have a tighter connection to physics, but still with the same mathematical rigor. So the cartoon version of the math-physics relationship currently is that modern theories like quantum mechanics just set the mathematical structure. So there is this sense that the mathematics comes before the physics, and the physics only comes later through an interpretation and finding observables and so on. If you look on Wikipedia, on the page for mathematical physics, you find this diagram. You see that there is the math, and from the math descends mathematical physics and also the ontology, which I don't understand how, and the physics is just a consequence of these things. And this is the wrong picture. The picture should be this. We have physics, we have a clear idea of what we want to describe. The physics is going to give us some physical requirement and a completely specified semantics. The semantics does not reach the math. The math loses the semantics. The math just uses symbols that doesn't know what they are. But the physical requirements can be translated into math, and they give us the mathematical theory. So we should have a structure like that. And if we did have a structure like that, we would not have a problem of interpretation or not knowing what the theory means, because we start from the physics and we know what the math means. And this is kind of what we did here, right? We started with a physical definition of what a composite system is, system dependencies. We put them in physical requirements that then led to the math, and we found the correct math. So what if we could take all of physics and do it like that? Now the issue is that to do that properly, we have to understand exactly what each mathematical construct physically represents. Like, we have to do from the ground up of every mathematical structure and do it, because the idea is that you can't just sprinkle physics on top of some mathematical structure and then suddenly have meaning. Meaning is something that you have to build in at every step. The correctness is something that you have to build in at every step. You can't just add it at the end. And so we would have to do it from the ground up, from everything, and it's going to take a long time, but we need to do it. And this is part of our bigger project called Assumptional Physics, and we actually do that, which is sort of much more in detail the type of things that we have done in this presentation. You identify a specific physical requirement, for example, that a scientific theory must be grounded in experimental verifiability. We encode that requirement in the math. We have to understand mathematically how to express it. And in that case, well, we basically say that every statement in the theory must be generated through ands or nots by a countable set of verifiable statements. Statements that have a test, and the test finishes in finite time and tells us the statement is true, if it is true. Once we have done that, we encode this in the math, and we get mathematical structure, and we can prove results in a mathematically clean way. We can see that the set of physically distinguishable cases form a T0 second countable topological space, and you might not know what a second countable topological space is, but the point is that that's the fundamental structure on which we construct differential geometry. All of the structure that we have in physics are of that kind. So it shouldn't be a surprise that we found that, that we defined that, but we know that those structures are tied to experimental verification. We can also prove that the set of physically distinguishable cases cannot exceed the cardinality of continuum. They can't be more than the points on a real line. Which means that if mathematicians go and look at all the other cardinalities, because you have infinitely many types of infinities, we know that in physics we only care about what happens up to continuums, and anything else which is valid research in mathematics is not going to be interesting for us. We also find that causal relationships are topologically continuous function, again giving a more precise sense of what we mean in physics by well-behaved function. It's a function that preserves experimental verification. So again, the idea is that we need to go through all the stacks of mathematics, and we do all things like we did in this presentation. You take some physics, spell out the requirements, encode them in the math, and prove results. And to do this, we need to coalesce ideas from different fields of physics, from classical, quantum, thermal, stat mech. We need to put all those things together in a whole coherent theory. We need a lot of ideas from mathematics, including foundations of mathematics. We can't really do foundations of physics and be completely not knowledgeable about the foundations of mathematics, because there are choices in the foundations of mathematics that may affect what are the type of things that we want to have in a physical theory. We need to understand those things. And computer science and philosophy of science and information theory, and there are lots of other things and a lot of perspectives that we need to put together. So if those type of questions are something that interests you, I would encourage you to look at our website and to get a little bit more familiar to the project. And if you think that this is a worthwhile project, it's something that needs to be done, and you want to help because you have some particular expertise in particular field, please let us know. And thank you again for the attention.